ink molecules. Okay, so it should diffuse in this direction. So we define this speed VI, so that unit should be meters per second. So this should be VI equal to the diffusion velocity plus the bulk velocity. Okay, and then this would be the diffusion, and this will be the bulk. Okay. So the bulk velocity is also called a transvection, right? So we just discussed about that. Okay. So sometimes this can be 0. Okay. Bulk velocity can be 0. Okay. So for the diffusion, that's so if we use this and then rearrange it, so we know that diffusion velocity equal to VI minus V. Okay, so this is VT. If you rechange this a little bit, okay. Okay, so then let's have some basic definitions for for some of these terms. Okay, so first of all, these bulk velocity. Okay, so the bulk velocity is the movement represent the movement of all the species in the liquid. Okay, so it has in this example, it has the water molecules, right? It also have the ink molecules, right? You have at least 2 molecules, in the system. Okay, one is water, one is the ink. Okay, so if I'm going to also join, some water here, and water is pretty uniform, right? At the very beginning, right? The water is everywhere, and it's pretty uniform. But the ink molecules is on like one location in the system, right? So that's why the ink molecule will diffuse. Eventually, it will be uniform everywhere. Okay. So let's define, the bulk velocity as average. Okay. So so for this V, we are going to define this bulk velocity as the so-called mass average velocity. Okay, so the bulk velocity is also called the mass average velocity. So how do we define this? So actually, this is defined as, so let me give you an example. Let's say I equal to 1 and 2. We only have 2 species, okay? So 1 is ink molecule, and 2 is water, okay? So we only have 2, okay? So clearly, this mass average velocity is based on ink and water, 1 and 2, right? So, so what do we have here? The definition is, the solution density. We have the total density, right? And then we are based on rho 1. So that is the density of the ink times the V1. Okay, that's the ink speed plus rho 2 times V2. Okay. So basically, the definition here is each species velocity times its density. We do a summation of all of them, and then we will divide it by the total density of the solution. Okay. So that's the mass average velocity that we are talking about. Okay. So that's the system that you have only 2 species. Okay. So what about you have n species? Okay. So whether if you have I equal to 1, 2, and n, how do we define it? Okay, so if we have n species, the density should define the mass average velocity should define as 1 over the total density, and then we do a summation from I equal to 1 to n. Okay, we're going to submit all of them. So rho I times Vi. Okay. So this is the the definition for the mass average velocity. This is also the velocity that we talk about as bulk velocity. Okay. And then we have another definition. This is based on the density, right? Density is more a parameter relates to the mass, right? And then in biological systems, we also use the molars, to describe the amount of molecules that we have, right? So we also have a different definition. We call it molar average velocity. Okay. And then we don't want to call it V. We want to call it a little bit different, because if we also call it V, then you cannot distinguish them, right? So we call it V star. Okay, we just do a star there. Okay. So when you see V star, it's describes the molar average velocity, right? So then V star is defined as if we have like system have only 2 molecules. So the definition is 1 over the, C is moles per meter cubic, right? So this relates to the, the molar concentration, right? And then times C1 times V1 plus C2 times V2. Okay, so this is molar concentration. Okay, and then if we have n molecules, so that's pretty much the same. So V star is defined as 1 over C. C is total molar concentration. That's going to count all the molecules. Okay, and then we are going to do we do the same thing. We do the summation of from 1 to n, all of them, and Ci times Vi. Okay. So this is the definition for the 2 velocities. Okay, one is called the mass average velocity, one is called the molar average velocity. Okay, so we use these velocities to describe the movement of the of the system. Okay, and for the molar average velocity, we can do an example here. Okay, so say you have a box, and then you have 2 different molecules. So I'm going to do some water. Okay, and then this is ink, and then I'm going to do some water. So I'm going to say this the volume for this box is 1 meter cubic. Okay, just give you an example, 1 meter cubic. And then if we do here, we can count what is the total molar concentration here. So we just count how many molecules we have, right? So we have 9 water molecules. And then for the ink, we have 7, right? So 7 plus 9, that would be 16, right? So then let's say just 16 molars. Okay, so we are doing like 16 molar 16 molars per meter cubit. Okay, so then this is the total concentration. Okay, molar concentration. So then what about C1? So C1 is ink. Then this is like we have 7, right? So C1 should be 7 molars per meter cubit. Okay, and then C2 should be, we have 9, right? So 9 molars per meter cubit. Okay, something like that. And then if they also give you the V1 relates to the ink, and then V2 relates to water, then you should be able to calculate V star. Okay, something like that. Any questions? Yeah, this is easy, right? This is relatively easy. Okay, so we have 2 definitions about the mass average velocity and then the molar average velocity. Now, we are going to define the most important parameters for this course. That is the flux. Okay, so let me write down the flux definition one more time. Okay, so when we say flux, we are talking about the amount of molecules crossing a unit area, in a given time. In a given unit of time. Okay, in a given unit of time. Okay, so the amount of molecules, you can use 2 ways to describe the amount of molecules, right? You can say, kilograms, okay, kilograms of ink, okay, or you can say, 10 molars, right? You can use molar to describe molecules, or you can use the mass, right? You can use both ways to describe it, okay? And then crossing a unit area in a given time, okay? So then these two are not going to change, right? The per meter squared per second, something like that. But because the amount of molecules, you can use 2 ways to describe it. So you will have 2 different flux. But these 2 flux can be converted from one to the other, right? If I'm going to tell you I have 1 molar water, so what is the mass? You can do it, right? So in high school, they already teach you how to do that, right? So you can base on the molecular weight, right? That's pretty easy to do conversion, right? So although it seems like we have 2 flux, but they can convert it from one to the other, okay? And then we are going to define both of them. And if we use mass to describe the amount of molecules, that's called a mass flux. If we use a molar system to describe the number of molecules, that's called a molar flux. Okay, so we have the mass flux and we have the molar flux. Okay. As I said, although it look like you have 2, but then, if you give me 1, and then I can convert it to the other, okay? So they are dependent on each other, okay? One can be converted to the other, okay? And why we have 2, right? If one can convert it to the other, why not just give us 1, right? That's like easier, right? So the reason we have 2 is because because in industry, people like to use one over the other. For example, in chemical engineering, so they use more of the mass flux, okay? And then in many biological systems, we would like to use molar flux more, okay? So it's just a preference. So it's better to understand, both of them, okay? So let's see each of them, okay? So then the mass flux, so we already talked about, flux for each of the species, right? So the definition for the mass flux is the species density, so rho I, times its velocity, vi. So if you use the density times its velocity, rho I times vi, this is defined as the mass flux, okay? And then mass flux, we call it Ni, okay? So this is the mass flux, okay? So let's do some unit analysis to see, if it's right, okay? And if it's like reach the flux unit, okay? So what is the density for rho I? So should it be, let's say, kilogram per meter cubic, okay? That's a unit for rho I, right? And then times what? Times VI, that's the meter per second, okay? So what do you got? So you got kilogram, and then you cancel 1 meter, right? You cancel 1. What do you got? Per meter squared per second, okay? Yes, exactly. We got the unit for flux, right? The amount of molecules that we use kilogram to describe it cross a unit area, okay, in a given time, okay? So yes, we reach the, the unit for flux, right? So we use its density times its velocity. So we call this new parameter Ni, and we call it mass flux, okay? So then what about molar flux? And ideas, if we use, what we have talked about, in the previous slide about this definition of mass average velocity and molar average velocity. So if you are going to define a molar flux, how are you going to do it?
Set it equal to CI/VI.
Yeah, that's right. Perfect. That's right. So the molar flux is defined as Ci times Vi. Okay, Ci times Vi. That's it. So very simple. So then we also call it, we need to give it something to represent CI/VI, right? So we call it Ni, but we don't want to be the same thing as Ni. So we use Ni. So the mass flux is the lowercase Ni, okay? The molar flux is, the capital case of Ni, okay? So we call it Ni. And then if you do the unit analysis, you will see the same thing, okay? So the CI is, the molars per meter cubic, right? It's the same thing, okay? Cool, so that's good. So we define the two flux. Okay, so next we are going to, let me do a summary of what's going on here. So this table will help you a little bit about what's going on for this course. So we are talking about velocity, right? So we talk about the velocity. And then the unit is meter per second, okay? And then we have different velocities, right? We have VI, okay? That's just your just species i's velocity, okay? So this VI is with respect to with respect to stationary axis. Okay. So you have VI. Okay. And then you can also use species i's velocity with respect to mass average velocity. Okay. So we can also do with respect to v, that's the mass average velocity. Or we can also do with respect to v star, that's the molar average velocity. Okay, so when we say with respect to means like as compared to, and then we want to see the difference between these two. Okay, so then we are doing like a vi. We're going to do a vi minus v, and then in this case we are going to do vi minus v star. Okay. So based on our first slide, you see if you do vi minus v or something like that, that's called the diffusion velocity. Okay. So you can see we have two different diffusion velocity. One is respect to v, that's the the mass average velocity. One is with respect to the v star. Okay. Okay, so we have these, and then we define the molar flux and the mass flux, right? So we define the molar flux. How do we define that? That's very easy, right? We use Ci times Vi, and then we call it Ni. Yeah, that's it. And then we also define the mass flux, right? How do we define that? We use the density times Vi. We call it lowercase ni, okay? Okay, so it's pretty clear, right? So for the Vi, and then you define the molar flux, Ni, and then you define the mass flux, lowercase ni, okay? But actually we can define, these four too, okay? So so what about here? What about here? Okay, what about here? We can also define similarly, okay? So let me do it for you, so then you understand, what's going on here. So you use this Vi with respect to the the stationary axis, that's Vi. What about with respect to the V, right? So we can do the same thing. What about we can also define like this, Vi minus V. We can also define Ci times Vi minus V star, okay? We can also define these. And the unit should be still molar flux, right? Because Vi minus V, the unit is still meter per second, right? The same thing. And what about here? We can also define rho I, Vi minus V, okay? And then we can also define rho I, Vi minus V star, okay? So we can define another 4 different flux, right? We can define another 4 different flux, okay? And, but the idea, the basic principle is the same. That is, you use the velocity and then times either density or molar concentration, okay? That's the underlying principle is pretty much similar, okay? But then we just define them differently, okay? So now you will have another 4 different flux, right? So, you do these different definitions, and then you have 4 different flux, and we call them differently, okay? So we call this one, we give it like, a letter to describe it. So we call it Ji, okay? So then how do we call this as compared to this, okay? So this one we call it total molar flux. And then this one we call it diffusive molar flux. Okay, diffusive molar flux. So why? Because Vi minus V, that's the diffusion velocity. Okay, that's why we call it diffusive molar flux. And then with respect to V, okay? And then what about this one? We also call it diffusive molar flux. And then we say with respect to V star, okay? So the second and the third, they all call it diffusive molar flux, but it's just with respect to V or V star, okay? So then how do we do this one? So we also call it Ji, okay? But then it cannot be the same, right? So we call it Ji star, okay? We call it Ji star because it's with respect to V star, okay? And then for the last two flux, it's easier because the difference between mass and molar is one is uppercase, one is a lowercase, right? So we just call it lowercase Ji, and then this one we call it lowercase Ji star. Okay. So in total, we have 6 flux parameters, right? Uppercase Ni, lowercase ni, uppercase Ji, lowercase ji, uppercase Ji star, and the lowercase Ji star. Okay, and they have different names. Okay, so we can also talk about the mass flux and then how do we name them, right? So the mass flux, we can try to name them. How do we call this? So this would be the total mass flux, right? So how about this one? We call it diffusive mass flux with respect to V. And then we call this diffusive mass flux with respect to V star, okay? Any questions? So I already present all the most important, parameters that we need in order to understand mass diffusion system. So, yeah, that's it. All the parameters are here.